Hello students, Mr. Courtney here. In this video, we're going to be talking about acids and bases, and more specifically, we will talk about the properties of acids and bases. Our objectives will be to discuss the following: properties of acids and bases, two models of acids and bases, and that is two models we use to define acids and bases, the relationship of the conjugate acid-base pairs, acid strength versus the strength of a conjugate base, and ionization of water. So we start off by just listing some properties of water, of acids, sorry. Acids are substances that usually have a sour or tart taste. In aqueous solutions, they are electrolytes. That means that they ionize in water and they are able to conduct electricity. They cause indicators to change colors. That is dependent on depending on the acidity of the solution, the indicators have a different color. Many metals will react with the acids to produce hydrogen gas. There also react with hydroxides to form a salt and water, what we call a neutralization reaction. Most acids their formulas begin with a hydrogen. Their pH is less than 7, or the pOH is greater than 7, and we'll talk about these two later on also. The H3O plus concentration, or the hydronium ion concentration, is greater than 1.0 times 10 to the negative 7. Or the OH, or the hydroxide concentration, is less than 1.0 by 10 to the minus 7. And they produce hydronium ions in water solutions. Now the bases, they produce hydroxide ions in water solutions. They have a bitter taste. They feel slippery, and they react with acids to form salt and water, as we talked about before, neutralization reaction. They cause indicators to change colors just like acids. They contain hydroxide ions. Many of them will contain hydroxide ions. They are also electrolytes in aqueous solutions. The pH will be greater than 7 and the pOH less than 7. For the hydronium ion concentration, it will be less than 1.0 by 10 to the minus 7. And the hydroxide ion concentration will be greater than 1.0 by 10 to the minus 7. All right, let's talk about the model to describe acids and bases. The first model was described by Svante Arrhenius. He was the first person to describe the nature of the acids and bases. And he defined an acid as any substance that produces hydrogen ions in solution. So for example, if we take hydrogen chloride gas and dissolve it in water, it ionizes to produce our hydrogen ions and our chloride ions. Because of this production of hydrogen ions, Arrhenius termed it an acid. Now, bases for Arrhenius produces hydroxide ions. So we take sodium hydroxide, dissolve it in water, it will produce our metal ion sodium and our polyatomic ion hydroxide. So again, according to the Arrhenius definition, acids produce hydrogen ions in solution and bases produce hydroxide ions. However, this concept is limited because it only allows for the definition of one kind of base. So a more general definition was developed by Johannes Bronsted and Thomas Lowry, which we call the Bronsted-Lowry definition. According to this, the Bronsted-Lowry definition, acids are proton donors, and when we say a proton, we talk about a hydrogen ion, and bases are proton acceptors. So in this model here, we have our acid and water is acting as our base. So our acid will donate a proton, water, which is acting as a base, will accept the proton to become the hydronium ion. Now the acid is just left with the A minus. So we have our acid, our base, our conjugate acid, and our conjugate base. So in the Bronsted-Lowry definition, acids are proton donors and bases are proton acceptors. So a conjugate acid is formed when the proton is transferred to the base. And a conjugate base is everything that remains from the acid after the loss of a proton. So here we have our acid. This is the proton on the acid, and this is our base. Now, when the acid loses this proton, it joins with this on the base. It joins with the base. So we now form our conjugate acid because the proton is transferred to the base. So that's our conjugate acid. and our conjugate base is what is left over from the acid after it has lost that proton. So here, acid without the proton is our conjugate base. So in terms of a conjugate acid-base pair, the two substances are related to each other by the donating and accepting of a single proton. What that means is that the difference between the conjugate acid and the base is just a single proton. So we have our base and our conjugate acid. So they are the same, except that the conjugate acid will have an extra proton with it. So that's our extra proton here, which this one only has 2, whereas this has 3 protons in it. So if we have these here and we ask which of the following represents a conjugate acid-base pairs, what we're looking for is the pairs that only differ by 1 proton or by a single hydrogen. So hydrogen fluoride and fluoride ions are different by only a single proton because hydrogen fluoride lost that proton to give us hydrogen ions and all fluoride ions. So these are conjugate acid-base pairs. Ammonium and ammonia are also conjugate base pairs because they only differ by a single proton. Ammonium lost that proton to give us ammonia. So these are our conjugate base pairs. Choice C would not be a conjugate acid-base pair because they do not differ by a single proton only. Now, if we have to write the conjugate base pairs for the following now. So all we see here is that we're losing a proton. So the loss of a proton, remember the conjugate acid-base pairs are going to be different by a single proton. So we're going to lose a proton from our acid, gives us our H plus and our Cl4 minus. So we have our ion here again. All we're going to do is differ by a single proton. So it loses our H plus to give us CH3 NH2, so our methyl amine. And that's our conjugate base for these acids. Now the strength of an acid. The strength of an acid depends on how much the acid is ionized in water. So in this reaction here, we have substances that act as base and substances that act as acid. So this is our acid and this is our base. And this reaction here is reversible, meaning that it can go both in the forward and reverse reaction, forward and reverse. So when we think about acids losing that proton and our base gaining that proton, then our conjugate acid and our conjugate base. So we have our conjugate acid and our conjugate base. Our conjugate base will also want to gain a proton. So that means there is competition between our conjugate base and the base for that proton. If the base has a stronger pull or a stronger attraction for the protons, then the reaction will proceed in the forward direction and the acid will dissociate. But if the conjugate base, has a stronger pull for that proton, then the reaction will proceed in the reverse direction to reform our acid, and that acid will not dissociate completely. It will only dissociate partially. So if the base, or if water in this case, has a stronger attraction for the proton, then we're going to create it's going to be a strong acid. So the acid will be completely ionized or completely dissociated. A strong acid. However, if the conjugate base has a stronger attraction for the protons, then the acid is only going to be partially ionized or partially dissociated. Hence, the acid is a weak acid. So we can also say here that the strength of an acid is determined by the position of its ionization or dissociation reaction. That means, does the dissociation lie far to the right or to the left? So if water in this case at the base has a stronger attraction for our protons, then the acid will dissociate. So it's a strong acid. But if our conjugate base has a stronger attraction for the proton, then it will lie to the left. So that will make it a weak acid. Not all because there is competition between the base and the conjugate base for that proton. So our strong acids. So initially, look at how many of the strong acids we have. We have approximately 10 of them, 10 molecules of that strong acid. Now they come at the end, they completely dissociate because we don't have any of them. All we have our H plus and our A minus. So we have our proton and our conjugate base. So that means the acid is completely dissociated. So the forward reaction predominates. And this will yield a weak conjugate base. What that means is the base is weaker than water. Its attraction for the proton is weaker than that of water, so it's a weak base. So strong acids will yield weak conjugate base. And they're also going to be strong electrolytes. That means that since it's completely dissociates, there are lots of ions present in solution. It'll be able to conduct electricity very well in solution. Whereas when we have a weak acid, they only partially dissociate. So we have our HB, but look, only one of it dissociates in solution. So we still have predominantly HB in solution. So that tells us that the conjugate base has a stronger attraction for the protons than water. So the reverse reaction predominates. That is, we're going from our ions back to our acid and our base. So it yields a strong base, or strong conjugate base, sorry. So stronger base, the conjugate base is stronger than water, meaning it has a stronger attraction for the protons than water. So a weak acid will yield a strong conjugate base, and it's also going to be a weak electrolyte. And it's a weak electrolyte because there are very few ions present in solution. Here are some common strong acids, and we've discussed these before: your sulfuric, hydrochloric, nitric, perchloric acid. And you notice that your hydrochloric, nitric, perchloric, they all have one proton. And these are called monoatomic acids because they only have one proton. Sorry, not monoatomic, monoprotic acids because they only contain one proton. Okay, so monoprotic. Whereas sulfuric acid is considered a diprotic because we have two protons present. So let's look at the dissociation of sulfuric acid in solution. So sulfuric acid, because it's diprotic, is going to lose one proton at a time. So when you start with sulfuric acid, it's going to completely dissociate to give us hydrogen sulfate. So sulfuric acid is a strong acid, but the hydrogen sulfate does not completely dissociate. Most of it is going to remain undissociated, so that makes it a weak acid. Sulfuric acid is a strong acid, but the ion it produces, or the acid produces when it dissolves or when it dissociates, hydrogen sulfate, is a weak acid because most of it still remains undissociated. How do we know it's an acid? So we still have that hydrogen present for it to donate. So it still has a proton to donate. Remember, acids are proton donors, or substances that produce protons or hydrogen ions in solution. Also, oxyacids. These are the acidic hydrogen is attached to an oxygen atom, like our organic acids. Or carboxylic acids. All these are going to be examples of weak acids. So think of something like vinegar, citric acid. All these are going to be weak acids. Strong bases. Just like strong acids, strong bases completely dissociate in aqueous solution. And they dissociate to produce metal ions and the hydroxide ion. So for example, if we had sodium hydroxide dissociating, it gives us the metal ion sodium and our hydroxide ion. Calcium hydroxide gives us the metal ion calcium and two hydroxide ions. Because we still have two hydroxide ions here, we need to balance it out. So again, strong bases, just like strong acids, will completely dissociate in solution. They're going to give us metal ions and a hydroxide ion. The weak bases, they do not completely dissociate in aqueous solution. So you have ammonia and methylamine. You're going to have approximately 99% of the ammonia remain undissociated, and somewhere approximately 1% ammonium and 1% hydroxide ion. So we just average it out there. Now, in terms of concentrated and dilute versus strong and weak, we have to understand that there is a difference. Concentration refers to the amount of the solute present in a given amount of solution. That is, how many moles of the solute we have in a given volume of solution. If we have a lot of it, then it's concentrated. If we have a small amount, then it's dilute. The strength of the acid or the base depends on what type of acid or base it is. So you can have a dilute solution of a strong acid or a strong base, and you can have a concentrated solution of a weak acid or a weak base. It just depends on the amount. So we need to know the difference between these two. So strong or weak tells us how well or how much it dissociates in solution. Does it completely or almost completely dissociate in solution? It's a strong base or a strong acid. If it does not completely or only partially dissociates, then it's a weak base or a weak acid. Water can act as an acid and a base because it's amphoteric, so it acts as both an acid and a base. And we'll talk about this is due to the fact that water is polar. Remember, hydrogen and oxygen share electrons, but because oxygen is more electronegative than hydrogen, it has a stronger pull on the electrons. So the oxygen will have a partial negative, the hydrogen has a partial positive. Because of that, water can both accept and donate protons. So it can act as a base in pure water at 25 degrees Celsius. The hydrogen ion concentration, or hydronium ion concentration, is equal to the hydroxide ion concentration. And that's approximately 1.0 by 10 to the minus 7. And here we see we can use these interchangeably, hydronium ion or hydrogen ion. They're essentially going to mean the same thing. So here water is acting as acid, water is acting as the base. This will be our conjugate acid, and this will be our conjugate base. Alright, the ion product constant, or Kw. Now if we take the concentration of the H3O plus and the concentration of the hydroxide ion and multiply them by each other, we get 1.0 by 10 to the minus 14 at 25 degrees Celsius. This is called the ion product constant, or the ion dissociation constant of water. So in any given sample of water, of pure water at 25 degrees Celsius, we will have 1.0 by 10 to the minus 7 molar hydronium ion concentration and 1.0 by 10 to the minus 7 molar hydroxide ion concentration. But because they're equal, they're going to cancel out each other. So there's no more acid or no more basic properties. So it's going to be considered a neutral solution. So if they're equal, it's a neutral solution. If you add an acid to the water, you're going to have a higher amount of protons or hydronium ions than hydroxide ions, so it's going to be an acidic solution. If your hydroxide ion concentration is greater than your hydronium ion concentration, then you're going to have a basic solution. That means a base must have been added to the water. Now, our Kw calculations. If I know the hydronium ion concentration or the hydroxide ion concentration, we can find the other. So for example, we're given the hydrogen ion concentration and we're asked to find the hydroxide ion concentration. So we use the relationship between these two, between our hydrogen ion and our hydroxide ion concentration. We know that the product of these two gives us Kw. And we know Kw is 10 to the minus 1.0 by 10 to the minus 14. So since I'm given hydrogen ion concentration, I rearrange my equation to solve for the hydroxide ion concentration, which gives us Kw divided by the hydrogen ion concentration. Kw is 1.0 by 10 to the minus 14, and I divide by my hydrogen ion concentration, which is 1.0 by 10 to the minus 5. And since the bases are the same, all we need to do is subtract our exponents. So that's negative 14 minus negative 5, or negative 14 plus 5. That gives us negative 9. So our hydroxide ion concentration is 1.0 by 10 to the negative 9. Now, in this case, we're given the hydroxide ion concentration, and we need to find the hydrogen ion concentration. So we look at the same process. We know the relationship between hydrogen ion and hydroxide ion concentration. We rearrange to find our hydrogen ion this time. So that is Kw divided by our hydroxide ion concentration. We know what Kw is, 1.0 by 10 to the minus 14. And we have our hydroxide ion concentration. And again, we're going to subtract our exponents since the bases are the same. So that's negative 14 minus negative 2, sorry. So that's 14 plus 2. So that gives us 1.0 by 10 to the negative 12. All right, so here we've discussed some properties of acids and bases. We talked about 2 models of acids and bases, the Arrhenius definition and the Bronsted-Lowry definition. We looked at the relationship between the conjugate base and acid pairs. We talked about acid and base strength, the strength of the acid versus the strength of the conjugate base. And we also talked about the ionization of water and ionization constant, Kw. So that takes us to the end of this video. Until next time, I'm out. Blessings.